Good morning, students. So today we will study about the semiconductor materials. The topics today we will discuss about the atomic structures, semiconductor, insulators, and conductors, and the covalent bonding, and lastly the conductions in semiconductor. So last week I taught all of you about this topic. Can anyone explain to me again about the first one, atomic structure?
Sir, I can answer.
Atom can be represented by the valence shell and a core. A core consists of all the inner shell and the nucleus. Let's take carbon atom as an example. The valence shell consists of 4 electrons, while the inner shell consists of 2 electrons. Insulator is a material which does not conduct electrical current. Conductor is a material that can easily conduct electrical current. Semiconductors is a material between conductors and insulators.
Okay, good. So, can anyone explain again with me the covalent bonding part? KELVIN, CHUN, NING?
Covalent bonding, an atom wants to achieve a novel gas configuration by sharing electrons. For example, a silicon atom, it has 4 pairs of covalent bonds with 4 neighboring atoms. For each atom, it will share 2 electrons to form covalent bond.
Okay, so what is the result of the
Bonds are
bonding?
held together by forming a solid substrate. The atoms are all electrically stable because their valence electrons are complete.
Okay, good. Very good, Kevin. So what is the N-type, P-type semiconductor? Can you explain with me, Michelle?
Doping is the process of creating N-type and P-type material. We can adding impurities atom to the intrinsic silicon or germanium to improve the conductivity of the semiconductor. There are 2 types of doping, that is, trivalent and pentavalent. For P-type material, that is a semiconductor that has added trivalent impurities. For N-type material, that is a semiconductor that has added pentavalent impurities. For P-type semiconductor, that is, trivalent impurities are added to silicon or germanium to increase the number of holes. For example, boron. Boron have 3 valence electrons to form covalent bond with 4 adjacent silicon atoms. A hole created when each trivalent atom is added. The number of holes can be controlled by the number of trivalent impurity atoms. The trivalent atom can take an electron, so the trivalent atom is called acceptor atom. Current carriers in P-type are holes, so holes are the majority carriers. For electron, that is minority carriers.
Now I will explain about the current in semiconductor.
The electron of an atom can exist only within prescribed energy band. Each cells around the nucleus correspond to a certain energy band and is separated from adjacent shell by gaps, in which no electron can exist. The figure shows the energy band diagram for an unexcited, which is no external energy such as heat, atom in a pure silicon crystal. This condition occurs only at temperature of absolute 0 Kelvin. In this figure, it shows the conduction electrons and hole. An intrinsic or pure silicon crystal at room temperature has sufficient heat or thermal energy for some valence electron to jump the gap from the valence band into the conduction band, becoming free electrons. Free electrons are also called conduction electrons. In the energy diagram, when an electron jumps from the conduction band to vacancy is left in the valence band within the crystal. This vacancy is called a hole. For every electron raised to the conduction band by external energy, there is only one left in the valence band, creating what is called an electron-hole pair. In the figure B, this bonding diagram is called the recombinations. Occur when a conduction band electron loses energy and fall back into a hole in the valence band. To summarize, a piece of intrinsic silicon at room temperature has at any instant a number of conduction band or free electrons that are unattached to any atom are essentially drifting random throughout the materials. There is also an equal number of holes in the valence band created when these electrons jump to the conduction band. It's called the electron and hole current. When a voltage is applied across a piece of intrinsic silicon as shown in the figure, the thermally generated free electrons in the conduction band, which are free to move randomly in the crystal structure, are now easily attracted toward the positive end, from here to the positive. This movement of free electron is one of the type of current in semiconductor conductive material is called electrocurrent. The electrocurrent in intrinsic silicon is produced by the movement of the thermally generated free electron. Another type of current occurs in the valence band where the hole created by the free electrons exists. Electrons remaining in the valence band are still attached to the free electron. However, a valence electron can move into a nearby hole with the little change in energy level, thus leaving to another hole where it came from. Effectively, the hole has moved from one place to another place. From here, the hole from this hole to another hole and move to the end.